In this video, I'm going to show you how to use the ratio test to tell whether an infinite series is convergent or divergent. Now, here's what the ratio test says. It says that for an infinite series whose terms are an, we can tell a lot about the behavior of the series by considering the magnitude of the ratio between two terms as the number of terms goes to infinity. Why don't we call that limit L? So L is the limit as n approaches infinity of the magnitude or absolute value of the ratio between two terms. Based on the value of that limit, L, we can make the following conclusions. First of all, if L is less than 1, then the series converges. On the other hand, if L is greater than 1, then the series diverges. On the other hand, if L is equal to 1, then the ratio test is inconclusive. In other words, no conclusion can be made about whether the series converges or diverges. Now, these three conditions might seem like a lot to remember, but you really don't have to memorize anything as long as you remember the intuition behind it. If L is the limit of the magnitude of the ratio between two terms as the number of terms goes to infinity, then you can think of the series as gradually looking more and more like a geometric series with ratio L. L is kind of like the number that you multiply a term by to get to the next term. If L is less than 1, then it's like you're multiplying by something that's less than 1 each time to get to the next term. So the terms would be getting smaller and smaller in magnitude, and therefore it would make sense that the series would converge. On the other hand, if L is greater than 1, then it's like the terms of the series keep getting bigger and bigger because their magnitude is multiplied by a factor that's greater than 1. So it would make sense that the series would diverge in that case. And lastly, it would also make sense that we'd be inconclusive when L equals 1, because whether the terms of the series are growing or shrinking in magnitude really depends whether L is approaching 1 from above or below. So in that case, we wouldn't know whether the terms of the series are growing or shrinking in magnitude, and therefore we couldn't tell whether it converges or diverges. Now, to be clear, if L equals 1, then the series could still converge, or it might still diverge. The ratio test just doesn't tell us what happens. We have to turn to some other test. So now that we know what the ratio test says, why don't we work an example? Let's use the ratio test to determine whether the series of 2 to the n over n factorial is convergent or divergent. Ultimately, this all boils down to computing the value of L. And to compute the value of L, we need to write the expressions for an plus 1 and an. An is pretty easy, that just comes from exactly what's inside of the series here. So an equals 2 to the n over n factorial. Now to get an plus 1, all we have to do is replace n with n plus 1 in this formula for an. So an plus 1 is equal to 2 to the n plus 1 over n plus 1 factorial. Now we just need to plug these two expressions into our limit. So we'll write that limit again. It's the limit as n approaches infinity of the absolute value of an plus 1, right here, 2 to the n plus 1 over n plus 1 factorial, divided by an. So divided by this expression here, 2 to the n over n factorial. Now remember that to divide fractions, all you have to do is flip the second fraction, take the reciprocal, and then it turns into multiplication. So this is really the limit of this first fraction, 2 to the n plus 1 over n plus 1 factorial, times the reciprocal n factorial over 2 to the n of the second fraction. Now, if you look on the diagonals here, 2 to the n plus 1 and 2 to the n, as well as n plus 1 factorial and n factorial, you might notice that there's a lot of things we can cancel. So let's write this out very explicitly. This is the limit as n approaches infinity of this same expression, but we'll write it a bit differently. This 2 to the n plus 1, we can write as 2 to the n times 2 to the 1, or just 2 to the n times 2. And then this n plus 1 factorial, that's just the product of all the numbers n plus 1, the number before that, which is n, the number before that, which is n minus 1, and so on all the way down to the number 1. Now, in the second term, n factorial, that's just the product of all the numbers n and downwards, so n times n minus 1 times so on all the way down to the number 1, and 2 to the n we can just leave the same. Now, the reason why this helps is because it lets us see what cancels here, like this 2 to the n and this 2 to the n here. Top, bottom cancels out. Likewise, n, n minus 1, so on down to 1, these all cancel with what's in the denominator here. So really all that's left over is this 2 over n plus 1. And that greatly simplifies the limit. This is a lot easier to take the limit of. So limit of the absolute value of 2 over n plus 1 as n approaches infinity. Well, the denominator is getting bigger and bigger, it's approaching infinity, but the numerator stays constant. So it's 2 over an increasingly large number, which goes to 0. Now, the final step, what does that say about the series? We found that L is equal to 0, so that means L is less than 1, which means the series converges. So that's our conclusion. L equals 0, and therefore the series is convergent. Let's try another example of using the ratio test to prove convergence or divergence. We'll use the ratio test to determine whether the series of 3 to the n times n over 2 to the n times n squared plus 1 is convergent or divergent. And again, as usual, this all boils down to computing the value of L. So all we have to do is plug in for an plus 1 and an, and that just comes from using this definition given in the series. This is the definition of an. Now, to get an plus 1, all we have to do is replace the n with n plus 1. So let's go ahead and do that. So 3 to the n plus 1 times n plus 1 over 2 to the n plus 1 times n plus 1 squared plus 1. So all we've done is replace all the n's in here with n plus 1's. And now we're dividing by an, so that's kind of like times the reciprocal of this fraction here. So the denominator now goes on top, 2 to the n times n squared plus 1, and then the numerator is now on the bottom, 3 to the n times n. Immediately we see that some things cancel. This 3 to the n plus 1 is just 3 to the n times 3 to the 1, so 3 to the n times 3, and that 3 to the n will cancel out with this 3 to n down here. So cancel the 3 to the n, and then all that's left over up top is 3. It's the same idea with this 2 to the n and 2 to the n plus 1. We can cancel out a 2 to the n from both of these terms, and what's left over is a 2. And now that we've canceled, let's go ahead and simplify this limit. So this is the limit as n approaches infinity of 3 times n plus 1, and then times that other numerator, n squared plus 1. And then in the denominator, we've got a 2 times n plus 1 squared plus 1 times n. Now to compute the limit, we just go ahead and expand it out. So this becomes the limit as n approaches infinity of 3 times n plus 1 times n squared plus 1. Well, n times n squared is n cubed. And then 1 times n squared is n squared. Then n times 1 is n. And then 1 times 1 is 1. And then in the denominator, we've got a 2, and then times n plus 1 squared, that makes n squared plus 2n plus 1, but we've got another plus 1, so really plus 2, and then that times n. We'll do one final round of simplification. multiply that 3 through in the numerator, so 3n cubed plus 3n squared plus 3n plus 3 all over. We'll multiply that 2 through the denominator as well as the n, so only 2n times everything. So we get 2n cubed plus 4n squared plus 4n. Now think back to limits. When you're taking the limit at infinity of a rational function consisting of two polynomials, you look at the highest degree terms in the numerator and denominator. If they have the same degree, which they do here, the power in n is 3 in both cases, then the limit is just the ratio of the leading coefficients. So this comes out to just 3 over 2. Well, the absolute value of that, which is still just 3 over 2. Okay, so we've got the value of L. Think back to the ratio test. 3/2 is bigger than 1, so that says the series diverges. So that's our conclusion. Because L is 3/2, which is bigger than 1, the series is divergent.